What if machine learning could help narrow down promising cannabis parent strains for a specific target profile? Instead of guessing which strains to breed together, we can use data to search for patterns in effects, flavors, and strain characteristics. In this episode, I will walk through a machine learning style breeding recommender that ranks strains and parent pairs. First, let's be clear about what this project is actually doing. We aren't predicting exact offspring genetics. We aren't guaranteeing a final terpene profile or the exact effects of a future cross. That is far more complex. Instead, we are doing something more practical. We are using machine learning to shortlist promising parent pairs. By identifying known characteristics in the dataset, we can find combinations that best align with our desired traits. The process starts with setting up our environment and importing the necessary tools for data analysis and scoring. We then load our specialized cannabis dataset, which contains detailed records of strains, their reported effects, and flavors. The first step is understanding the raw data. Here, the notebook inspects the dataset structure and previews columns. This matters because strain datasets are often messy and inconsistent, requiring careful handling before processing. The model needs to understand what information is available, such as terpene notes, effects, and lineage metadata. Next, the notebook defines a target breeding profile. This is one of the most important parts of the entire workflow. Instead of searching blindly, the model is given a profile to aim for. Here, we target specific effects and flavors. We also specify the desired strain type, in this case, sativa, and the preferred growing environment. We can even adjust scoring weights to prioritize certain traits, like flavor, over others, such as environmental suitability. This turns the project into a recommendation problem. Which strains best align with this specific target? Once the profile is set, the model begins by ranking individual strains based on how well they match our criteria. These scores are derived from similarity in effects, flavor notes, and even descriptive keywords in the metadata. This first ranking creates a shortlist. It helps identify which single strains are already close to the desired direction. Even before we start pairing, these individual rankings provide a solid foundation for our search. This is useful because breeding strategy often starts with parent selection. We want the best possible starting point. By identifying strains that already align with the goal, we significantly reduce the search space for our breeding project. Instead of looking at thousands of possibilities, the model surfaces the strains that are most relevant to the target. After ranking individuals, the workflow moves to the more interesting step: ranking parent pairs. Here, the notebook combines candidate strains and scores how well each pair covers the desired target profile. This includes checking if the combined profile covers all the requested effects and flavor notes we specified earlier. The result is a ranked list of pairs that may be worth exploring further in an actual breeding program. This is where the recommender becomes especially useful. A single strain might only partially match our goals, but a pair can complement each other. One parent might provide the effect, while the other brings the flavor. Or perhaps one parent is better suited for the climate, while the other contributes to the terpene profile. The model rewards combinations that achieve better coverage across all target dimensions simultaneously. This makes the pairing view much more useful than simply picking the top single strain from the first list. To understand why a pair ranked highly, we break the score into parts. This makes the model more interpretable. This table shows performance across multiple components, including effects and flavor coverage for each pair. We also see how they match our environmental and climate preferences, providing a holistic view of the match. Even text similarity and diversity bonuses are calculated, ensuring the model isn't just focusing on one area. Instead of just seeing a final score, we can see exactly what contributed to that recommendation. The coverage plot makes this logic even clearer. It shows how the top pairs compare across several dimensions. Some pairs may perform strongly on effects, while others stand out in flavor or descriptive similarity. The plot allows us to visualize the trade-offs and strengths of each candidate pair at a single glance. The best pairs tend to be the ones that perform well across multiple categories, not just relying on one. This is the right moment to be clear about the limits of this workflow. It is a guide, not a crystal ball. The system does not tell us exactly what the offspring will become. It does not replace real breeding knowledge. Phenotype observation and lab testing are still essential. What this does is help organize the search. It helps identify promising combinations worth exploring based on the information available in the dataset. The final summary brings everything together. We start by defining a specific target breeding profile. We then rank the top individual strains that best match those goals through multiple similarity metrics. From there, we surface the most promising parent pairs based on their combined profile coverage. The main takeaway is simple. Machine learning can be a powerful assistant in the breeding selection process. It doesn't guarantee the result, but it points you toward combinations that are most aligned with your goals. If you want more code-driven cannabis and machine learning experiments like this, be sure to subscribe. Stay tuned for the next session. Happy breeding!